Hello everybody. So far we have discussed on the elastic model or maybe elasticity problem related to the manufacturing processes. Now we will try to discuss the plastic deformation behavior and what we can develop the different laws of plasticity. Specifically the more generally we use the von Mises yield condition during the plastic deformation of a particular component. So, we will try to explore these things and we try to develop how the von Mises yield condition actually comes and what we can utilize these things for the development of the any kind of mathematical model. So, plasticity, we know that the data normally if we conduct one universal tensile testing machine, the tensile testing of a specimen, we apply the load in particular single direction and then we define this is the yield point, particularly the yield point is the transition point between elastic deformation and plastic deformation. Therefore, what way normally most of the material actually behaves within the elastic limit, the stress is proportional to the strain, and based on that we define the Young's modulus and other material parameters, and we utilize all these things in the development of the elastic model. But in actual practical application, most of the engineering materials behave like elastoplastic material. That means in the plastic deformation, what we can represent the plastic deformation, and specifically it is one dimension, it is very and if we want to develop from the experiment, we can easily extract the data for the plastic deformation. But if it is 3-dimensional situation, say in machine component or in any particular component, it is subjected to 3-dimensional stress state of the stress. Then what we can define, we can explain the plastic behavior or plasticity of this particular material. So, therefore, it is very important to know the material behavior, specifically very large strain forming operation. So, that means plastic zone is to some very large extent. In that cases, first task is to define the yield surface. What way we can define the yield surface? So, yield may be a point when we apply the unidirectional load, but it may not be a point when it is subject to some kind of the say more than one load is acting, one direction load is acting. For example, both sigma x and sigma y is acting and having two principal stresses for a particular stress situation. In that cases we can, or maybe more than two, that means 3-dimensional, 3 principal stresses we can evaluate, non-zero principal stresses exist in a particular situation. In that cases we can define the yield surface rather than yield point. So, therefore, first part of the plasticity model or plasticity analysis, the how to define the yield surface. Second point is that to sustain the plastic deformation, we need to put some condition that is called normality condition or material stability, and that material stability is analogous to that plastic deformation behavior. So, what we can establish the material stability or normality condition we put to sustain the plastic deformation. Then flow curve also. So, in plastic deformation then we define the flow curve, but to basically flow curve behavior is necessary, we try to develop the plasticity model, but we will be focusing most on the yield surface and this normality condition. And of course, once we define the yield surface, then what we can incorporate the effect of the strain hardening, because we have seen in the stress strain diagram, this is within the this is the elastic limit, stress is proportional to the strain, but beyond that, there if you this within the plastic zone, there is a increment each and every point. If you see, there is an increment of the strain. So, that strain as well as the when there is increment of the strain, that means plastically deform the material, the strength level also increases, the stress level also increases. So, that is because of the material having the strain hardening effect. So, in the in single point it is well defined, the strain hardening effect can be defined, but if it is a surface, what we can define the strain hardening effect, that means how the yield surface evolves during the plastic deformation process, then that way, so that we can take care of the strain hardening effect of a particular material specific to one in plasticity theory. So, therefore, strain hardening effect we will try to look how we can incorporate. So, therefore, flow theory of the plasticity means the flow behavior plastic deformation happens at the so basically we are interested to this zone, plastic deformation zone. So, analysis in plasticity model normally done in the incremental mode. So, that means incremental strain, we look into the incremental strain that depends on the stress value. So, suppose this is the plastic deformation zone. So, we normally divide in the small components, small incremental strain. So, this strain and stress, and then that incremental strain and depends on the stress value. So, we predict, because in plastic deformation if we look into that each and every elemental thing there is a change of the slope. So, that continuous change of the slope. So, that is why the accuracy of the calculation depends on how small we can take this elemental strain. So, that in incremental mode normally stress analysis or plasticity model normally develops using the incremental strain. Now, normally we use the stress induces the strain rate, which is analogous to the pressure and the velocity. So, if there is a pressure difference, then only fluid flow and with certain velocity. So, here also if stress induces also strain rate, that also strain rate also having some influence in the plastic deformation behavior, strain rate. So, therefore, two stage behavior, elastic and plastic, but is normally implied in the sense that of course we normally we do the elastoplastic analysis. So, there is a elastoplastic analysis in most of the manufacturing process. For example, in case of bending process. So, in bending process also there must be some amount of the elastic spring back effect. So, we need to incorporate that the elastic spring back effect, then only we can get the actual plastic deformation needed to get particular bend angle. That we will discuss in the during the material forming process module there. But of course, that elastic spring back effect is basically nothing but the material having some kind of the elastic component. So, that once even if we know already discussed that even if you do in the plastic deformation zone. So, when you remove the load at particular point, there is some recovery will be there. That recovery because of the material having the some amount of the elastic properties. So, that is why we can represent the material behavior in the sense of that either elastoplastic material kind of this thing, or perfectly plastic material, or we can say perfectly elastic material. So, based on the stress strain diagram of a particular material. So, that kind of situation we can explain here also. For example, two stress strain curve for a ductile material. If you see the two stress strain curve ductile, we have already discussed two stress strain curve of a ductile material. Here we can see that sigma 0 is the yield stress value here, and from here to this is a plastic deformation. Now, if there is at point A, if we remove the load, then it will come back to this point. So, therefore, this is the amount is the permanent strain exist within the material, because it crossed the yield point. So, permanent strain must exist, but this amount strain represents the elastic recovery during this deformation process. So, this is typically called elastoplastic material behavior, or this is typical stress strain diagram of a particular ductile material, and most of the engineering materials actually follows this kind of stress strain behavior. Now, for example, if this is the situation, stress strain curve is something like that. Here if the remove the load and reload it, there is some gap exists. So, then that is represented in the stress strain, it happens during the hysteresis. So, that we see that if the this is representation of the hysteresis of a particular stress strain diagram in typical nature, and of course, we have already discussed in terms of material properties. If the area is more, that means material is having good damping properties, it having the capability of absorbing the vibratory load during the application. So, that is why it is a typical behavior of the material. So, that if this curve is not exactly linear and parallel to the elastic portion of the curve. So, then some sort of gap is there. So, that gap represents some kind of the material properties. If stress strain behavior is something like that, is a applying the tensile load reach this point and we just reverse the load from tensile load to we apply the, it is come back to this point, remove the load, and if we apply the compressive load, then it will reach up to this point. So, therefore, yield point in the tensile load and yield point in the compressive load are different. So, this type of situation arise, then we say this is the material is having Bausinger effect. So, if we consider the Bausinger effect, that means if the yield point in tensile load and yield point in compressive load both are same, then we can say the material having no Bausinger effect. Similarly, This is the stress strain diagram of a particular material. This is called the rigid ideal plastic material. So, that means there is no elastic component here, directly it starts from the plastic deformation here at this point, and that there is no strain hardening effect also, because this curve line is parallel to the strain axis. So, therefore, this type of behavior material is called the rigid ideal plastic material behavior. And of course, we can see that ideal plastic material with the elastic region, that is also, that means this part, the linear part, that is called the elastic part, exists within material, but there is no strain hardening effect, it is simply parallel to the during the plastic deformation zone. So, this is called the ideal plastic material with the elastic region. So, this type of behavior. Of course, piecewise linear, that means here linear component is there, and we can say another linear part is there, piecewise, we can say also bilinear curve also, but of course, it is having some strain hardening effect, because this line is not exactly parallel to the strain axis, it is having some slope with respect to the having some slope. That is why it is slope, means that some positive slope exists in the during the plastic second linear part, it indicates that material having the strain hardening effect. So, these are the typical material behavior we can represent by simple stress strain diagram and having the different type of the different nature. So, based on that we can develop the material model and we can analyze the deformation behavior of a particular material. Now, why we are interested to know that yield point of a particular situation, because in apply the yielding condition, the resistance of a material given by the yield strength. Of course, yield criteria, we need to find out the yielding criteria, that yielding means just starting of the plastic deformation zone. So, therefore, it is important to know at which point the elastic deformation plastic deformation starts. That is why we always try to find out what is the yielding condition or yielding criteria for a particular material. Of course, even if we define the fracture criteria, then we should know what is the ultimate tensile strength of a particular material is normally used. So, therefore, ultimate tensile strength is normally used to decide the fracture criteria of a particular component. So, that is why yield stress and ultimate tensile strength having some significance and to analyze the failure criteria of a particular material. So, therefore, failure criteria of isotopic material is often expressed in the mathematical form, that failure criteria we design the functional form of the failure criteria of is a sigma 1, sigma 2 and sigma 3. These are the 3 principal stresses. So, that means we can find out that it is a function of the so for example, in a particular component it is subjected to some different kind of the loading and combined loading, but we represent it in terms of the stress tensor. We represent the 6 components of the shear stress and 3 components of the normal stress and 3 components of the shear stress. So, total 6 components of the shear stress that can be represented in terms of the principal stress component, that sigma 1, sigma 2 and sigma 3. So, then you can try to decide the failure criteria from the theory analysis with the external applied load, we can find out what are the principal stresses acting for a particular material, and then for the same material we have the data for the different values of the, for example, sigma c is the maybe yield strength or maybe ultimate tensile strength, but that ultimate tensile strength and yield strength is actually defined in a uniaxial tensile testing of a particular specimen or particular sample. So, therefore, failure criteria either yielding or a fracture we can decide which is predicted to occur when a specific mathematical function f is equal to the failure strength from a uniaxial tensile system. So, these data are available for a particular material or well defined, but this data is not defined. This is the during the process it is the load is acting to this component, and then we can based from there we can find out the principal stresses and we can compare whether it is fracture or yielding happens or not, just looking by just comparing the experimental data for the same material. Now, usually effective stress, that means when we say the effective stress, or we can say that effective stress is significant because effective stress can be represented one single numerical value. So, that can be a function of sigma 1, sigma 2 and sigma 3, because sigma 1, sigma 2 and sigma 3 are the principal stresses, and these principal stresses are basically defined sigma y, sigma z, that acts tau x y, tau y z, tau z x. So, therefore, this is the original state of the stress acting for a particular material at a certain situation. From there we can finding out the functional form of this sigma 1, sigma 2 in terms of principal stresses, and then based on that we decide the function, what may be the functional form of this principal stresses, such that it can be represented in terms of the equivalent stress or that is representative of the single value. Then when we represent the single value, then we compare this single value stress with respect to the experimental value. It may be either C or sigma y. So, then if we compare this way, this is theoretically estimated, we convert it single value, and then we compare with the experimental value. Then we decide whether we can fit the criteria, whether there is a failure happens or yielding happens or not for a particular material. So, this is the normal procedure to find out, to compare this thing, the experimental value and the theoretical value. But of course, what may be the functional form of this this principle as a function of principal stress, this functional form is to decide depending upon the different hypothetical processes or some assumptions. Based on that we can predict the different kind of theory, and from that theory we can define the functional form. Such theory, one of the such theories I will try to explain, that what we can define this functional form such that we can decide the failure criteria or yield criteria for a particular material. Now, before that, what we can define the yield surface of a particular material. So, it is well defined that yield point of a particular material, if we do the uniaxial tensile testing, that means material is subjected to only one directional load or one directional stress. Based on that we can define the yield point. But in practical, the material is not subjected to the uniaxial loading condition. Maybe material is most of the cases practically the multiaxial loading condition. So, when there is a multiaxial loading condition, then how we can define the yield surface. So, for example, suppose sigma 1 is acting on a particular element, at the same time sigma 2 is also acting. So, in these cases what do we define the yield stress value? So, practical approach is that we can decide, we can keep either sigma 1 or sigma 2 as a constant value. For example, we consider sigma 2 as a constant fixed value. Then if we conduct the stress percent, if we vary the sigma 1 for a particular sigma 2, we can get a single curve like this. So, maybe this is the failure point, ideal condition. Now, if we change the again if we change the sigma 2 value, if we increase or decrease the next level increment or decrement of the sigma 2 value, then again we conduct the tensile testing, then we can get this curve, this similar curve may be different, and this is the sigma 2, different values of the sigma 2. So, in that way at the different value of the sigma 2 we can get the stress versus strain, that means sigma 1 versus epsilon 1, a different curve. So, therefore, it is a different curve, and that in each and every different curve there may be some yield point. So, that yield point when you join together, then it creates a kind of the curve if it is 2 dimensional. If it is 3 dimensional, then that can be represented in the form of a surface. So, therefore, but this changing the sigma 2, maybe there is a change, the gap, this is the one yield point, this is another yield point may happen. And of course, if we try to experimentally define all this thing at this yield surface, or maybe it's a huge number of experiments, but just by changing manually the different values of the sigma 2, and of course, if it is 3 dimensional, then it becomes more complicated, because there are so many combination of a particular, because we have to keep this for a fixed value of sigma 2 and sigma 3, we can conduct the experiment for varying the sigma 1. So, therefore, with this combination, the lots of combination is possible, and therefore, we need to define lots of experiments to define the yield surface. So, therefore, even if we do conduct the experiment, then not exactly, there is a range actually when you changing sigma 2 dot next value. So, it is a range of the stress is. So, suppose if it is a 2 dimensional, the sigma 1 and sigma 2 on the stress axis, if we plot it, this is the curve that represents the yield stress value. So, it is a within that elastic, beyond that plastic deformation. So, that way, but it is not exactly, if we are not fitting exactly curve, there is some variation actually happens during this process, but we roughly estimate this can be the closed curve on a stress axis that represents the yield curve when it is subjected to 2 dimensional state of the stress. Similarly, if it is 3 dimensional, then we define as a surface. So, that, but question is that we increase that delta sigma 1, delta sigma 2 to conduct the experiment, but what may be the amount as minimum as possible, then we can create the a good estimation of the yield surface profile or yield curve, but in that cases we need a lots of experiment. So, therefore, see it is actually vary depending upon the delta sigma 1 sigma 2, it is actually in this it is vary the yield profile. So, we approximate it as a curve. So, some averaging value. Of course, presence of the strain hardening requires a new specimen for each and every specimen. Therefore, since there is a strain hardening effect is also there in elastoplastic material. So, therefore, we need to conduct more number of experiment, and of course, the surface may not smooth also, it is a kind of curvature is there. So, therefore, most of the measurement of the yield surface are made with the radial path. So, that means in this direction radial path we can measure most of the yield surface. Therefore, it is almost impossible to conduct the experiment for different conditions by changing sigma 1 sigma 2 for a particular material. Then people have developed different theoretical analysis of this thing to predict the yield surface for a particular material, of course, just looking into the analogy of a particular during the experimental process. So, we can assume the yield function, we assume that yield surface is a closed and smooth surface rather than some wavy surface. Now, once we assume the yield surface is a closed smooth surface for the 3-dimensional state of the stress, therefore, at particular instant the yield surface can be defined is as a in the functional form. For example, F sigma ij is the index form, sigma ij is the stress tensor. So, it is having the all those components 1, 2, 3, 4, 5, 6, 7, 8, 9 of the 9 components will be there. So, therefore, it is a function of assume that sigma 1 1 sigma 2 2 3 3, that means normal stress and 3 shear stress components and equal to k is a constant. Now, this is the functional form, we assume this is the functional form because all stress components having the contribution to the yielding of a particular component when it is subjected to 3-dimensional state of the stress. Now, if we assume that isotropic material, so isotropic material means same properties in all direction. If we assume these things, so therefore, it is possible to write in terms of the principal stresses. So, once we assume it is a isotropic properties of a material, isotropic material, then once we assume the isotropic material, this functional form is reduced in terms of the principal stresses sigma 1, sigma 2, sigma 3. So, therefore, once we as a function of sigma 2, sigma 1, sigma 2, sigma 3 in terms of the principal stresses, then we can represent that this is the what we can find out the principal stresses, then that if you having this stress component, then from here we can find out the characteristic equation, and from this characteristic equation we can form the cubic equation. This cubic equation is in this form, and where I1, I2 and I3 are the stress invariant, and this lambda is the basically roots of this equation. So, these roots of these equations are the principal stresses. This equal to 0 or algebraic form of this equation can be represented in that way, sigma minus lambda 1, sigma minus lambda 2, sigma minus lambda 3. So, here lambda 1, lambda 2, lambda 3 are the roots of this equation, and it is a cubic equation for that. So, this is the way to represent this stress component in terms of the principal stress components, and that we are just simply representing the cubic equation such that this cubic equation, the roots of the cubic equation represents the principal stresses of a particular situation. Now, stress invariant we have already discussed, but stress invariant just for I1 equal to in terms of the principal stresses, these are the stress invariants sigma 1, sigma 2, sigma 3, I2 also sigma 1, sigma 2, sigma 2, sigma 3 plus sigma 3, sigma 1, and I3 is the sigma 1, sigma 2, sigma. These are the stress invariant of this cubic equation. Now, isotropic material, so therefore, K functional form is a function of for isotropic material we can use with the original stress state to principal stress state, function of this, or this a sigma 1, sigma 2, sigma 3 as a function of one way, or we can say it is a function of sigma 1 or I1, I2, I3, because I1, I2, I3 actually represented in terms of the all the stress invariance is in terms of the principal stresses sigma 1, sigma 2 and sigma 3. So, therefore, isotropic material we can represent K the functional form either as a function of stress invariant or K as a function of all the 3 principal stress components. Now, to a very high accuracy plastic deformation, we have already discussed that stress components can be decomposed into two parts. One is the hydrostatic stress component and the deviatoric stress component, and we have already discussed that hydrostatic stress components having no influence on the plastic deformation. So, therefore, since yielding having no influence on the hydrostatic stress component, therefore, we can separate out this stress component, original stress component, to the deviatoric stress component, because the yielding depends on the deviatoric stress component and it is independent of the hydrostatic stress component. So, therefore, solids under hydrostatic pressure do not deform plastically, therefore, the hydrostatic stress having no influence on the plastic deformation. Therefore, we just rule out the hydrostatic stress component from the original stress state. So, therefore, if you look into only the deviatoric component, so deviatoric component is the sigma 1 is the actual principal stress minus the hydrostatic stress component. Similarly, we represent the all three deviatoric stress components in this way, such that hydrostatic stress component is the average of all these things, that we have already discussed. Now, we can say that K is a function of all the stress invariant I1, I2 and I3 and original stress state, but when we convert into the deviatoric stress component I1d, I2d and I3d, from here to here we can see, since hydrostatic component having no role on the plastic deformation yielding, so you try to finding out the yield criteria, then we can convert it in from the original stress to the only deviatoric stress component. But if you look into the deviatoric stress invariant here I1d, so I1d we can see the I1d actually 0, if we find out that I1d sigma 1, sigma 2, sigma 3, and then in terms of the deviatoric component I1d is actually I1d should be sigma 1d plus sigma 2d plus sigma 3d. If we add all these components d, so here we can find out that it becomes actually 0. So, then if it is 0, because sigma 1d equal to 0, then we can say the K is a function of only the I2d and I3d. That means, this functional form we can reduce that only two stress invariant and two stress deviatoric stress invariant I2d and I3d. So, therefore, for isotopic material and pressure independent material in the sense that pressure does not influence the yielding of a particular material. So, therefore, for isotopic pressure independent material, the functional form can be reduced into this K F I2d I3d. Now, the plastic response of the metals is often the plastic response we observe most of the engineering materials, that there is no Bausinger effect. That means, the yield stress in tensile and yield stress in compressive load are same. So, in that sense we can say the metal is having no Bausinger effect. So, since the metal having no Bausinger effect, then we can say that in analogy to metal having no Bausinger effect, we can say that can be mathematically said that I2d sigma ij equal to I2d minus sigma ij. So, this is actually is a even function, that I3d sigma ij, I3d sigma ij. So, this when you represent this mathematical expression, it actually represents the, if these are equal, changing the sign, the function is the even function. So, therefore, even function in the sense that since the loading in the tensile and compressive yield stress value, compressive yield stress value in the negative sign will same, but same magnitude, the same magnitude, but signs are different, mathematically we can say the function should be even function. So, therefore, if to indicate no Bausinger effect, that means the functional form should be the even functions. Now, it should satisfy these two, that indicates mathematically that no Bausinger effect exists here. But if we look into that functional from the I2 and I3 or I2d or I3d, we can, if we see that if we change the sign of the sigma 1, sigma 2 and sigma 3 together, then we can see there is no change of the sign in the functional form here. If we change sigma, if we replace sigma 1 equal to minus sigma 1, sigma 2 equal to minus sigma 2 and sigma 3 equal to minus sigma 3. If we put it here, then it becomes the same expression, but if we put here, then it changes sign, I3 becomes now minus sigma 1, sigma 2 and sigma 3, or same thing for deviatory component. Therefore, I3 does not satisfy this conditions. That means in this in mathematical sense this functional form is not even function, it is not satisfying. So, therefore, we can say for isotropic pressure independent, if there is no Bausinger effect, then the functional form can be represented only on the second stress invariant, because it is not satisfying. It means that it is not satisfying, means it is not satisfying mathematically, means it is not satisfying that Bausinger effect. Therefore, we can say we can reduce further the functional form is in the form of only second invariant. Now, if we can do the further calculation manipulation of the second invariant in that way, sigma 1, sigma 2, sigma 2, sigma 3, sigma 3, sigma 1 d deviatory component. If we put all these values, we can find out in terms of the principal stresses, this is the expression for that, and we can convert it in the 1/6 of this is the expression for that. Now, k becomes finally as function of sigma to I to d second stress invariant, and it is a in terms of this is the functional form, or in terms of the principal stress, or this is the in terms of the original initial stress. So, therefore, we can see that factor k, we can say in this way that it is the functional form, but factor 1/6 is included in the arbitrary constant. So, it is a we can just maintaining the constant, but the functional form is this one. So, this functional form actually represents the well known the von-Mises yield function, and this von-Mises yield function is one of the most widely used in the plasticity model, and we can see that how this functional form actually develops by assuming the several functions. But this functional form actually valid with the assumptions that material in practically material is isotropic material and the yielding is pressure independent, and if there is no Bausinger effect, then only the yield functional form can be represented in this way. Now, we can cross check also that this functional form of the yield surface. So, if you see the isotropic material the properties is independent of the direction, therefore, written in the principal stresses, and each principal stresses enters in the functional form equivalently, in the sense that if you see all components sigma 1, sigma 2, sigma 1, sigma 3 and sigma 2, sigma 1 all enters the equivalent, there is no constant or something like that. So, therefore, it is a validating the isotropic material properties, and the pressure independent means mathematically you can say adding a constant term to the principal stresses does not change the functional form. If we add that constant term in all sigma 1 and equal to say sigma 1 plus some constant term, similarly sigma 2 equal to sigma 2 plus and sigma 3 equal to sigma 3 plus p. If we put add constant term and if we put here also, then there is no change in the functional form. So, that means the yielding actually independent of the pressure, and of course, the Bausinger effect, can be proved that if sign of the stresses does not alter the function. If you change the sign of the stresses sigma 1 to minus sigma 1, sigma 2 minus sigma 2 and sigma 3 to minus sigma 3, the functional form remains the same. That means there is no Bausinger effect in this expression. So, we can represent this is the yielding in graphically the yielding, this is the yield surface, and this axis represents the sigma 1 equal to sigma 2 and sigma 3, and this is the yield surface, and that yield surface can be here also. That means it is a value actually increasing, it is independent of the hydrostatic stress component. Now, 2-dimensional, that is from 3-dimensional yield stress components to 2-dimensional curve, we try to discuss that things. For example, plane stress plasticity problem sigma 3 equal to 0, then what may be the yield surface functional form? The functional form k equal to sigma 1 minus sigma 2 equal to 0, sigma 1 minus sigma 2 square plus sigma 1 minus sigma 3, just simply sigma 3 equal to 0. This is the yield surface functional form of the yield surface yield curve for a 2-dimensional stress state. Now, we can find out the value of the k also. This is the k is the this thing that k can be normally decided from the experimental observation. What we can do these things, for example, we assume the uniaxial tensile testing, the situation uniaxial testing the sigma 1 equal to sigma bar, say for example, this is the yield stress value, uniaxial tensile testing sigma 2 sigma 3 equal to 0. So, if we put all this condition this expression, then we can find out that k equal to twice sigma bar square or sigma bar equal to root over of k by 2. So, this is the k value of this thing. So, now if we find out twice k value sigma bar square equal to sigma 1 minus sigma 2 square plus sigma 1 square plus sigma 2 square. So, this is the yield surface functional form, and this is the situation, and we can define the K by simply doing it into the uniaxial tensile stressing specimen. So, therefore, this sigma bar is actually, this is the functional form, and this sigma bar is the yield stress, normal yield stress of a particular material. Similarly, K can have the different values if you do the biaxial tensile testing. So, in biaxial tension, if you see sigma 1, sigma 2 both are same equal to sigma bar and sigma 3 equal to 0, then we can find out sigma bar equal to this expression. Similarly, if pure shear condition, we can conduct the experiment. Pure shear condition, the situation is that sigma 2 equal to minus sigma 1 and sigma 3 equal to 0, and in these cases we can find out that sigma bar equal to root over K by 6. So, therefore, the K value or expression of this yield curve can be modified looking into the different type of the experimental observation. So, for example, uniaxial tensile testing, biaxial, pure shear, all these different cases K's are different value. Now, we can see if this is the sigma 1 and this is sigma 2 axis, and if we put this is the point represents the uniaxial root over K by 2, and this represents the biaxial, here the sigma bar equal to K by root over of K by 2, and of course, pure shear condition, this is the point, and this axis represents the sigma 1 sigma axis. This is the major axis of an ellipse. So, and this is the minor axis of an ellipse. So, this is the locus of all this point such that minor to major axis equal to root over 2 by 3. So, this way we can represent the different value of the K and the different functional form of a yield curve and the different situation. Now, equivalent or effective stress, the constant K determines the size of the yield surface, definitely the size of the yield surface, and that yield surface, and if we put the value of the K at the from the different experimental value, that actually decides the yield surface size as opposed to the shape. A shape is the decided by this functional form, but K defines the actually size of the yield surface. Now, K represents the hardness. Now, if there is a change of the value, for example, we can conduct the sigma 1 is the, for example, the value of the from the uniaxial tensile testing we can find out the sigma 1 value, but uniaxial tensile testing value, this is the yield point, the first yield point, just elastic to plastic zone sigma 1, for example. Then with the strain hardening effect it changes. So, therefore, if we incorporate the strain hardening effect, the yield surface is about something like that, it is the first yield point, then this is next yield point. Next yield point means this is moves from here to here because of the strain hardening effect of a particular material. Similarly, it changes from here to here, from here to here. The strain hardening effect can be incorporated by simply changing the size, and that size change is decided by what is the value of K we are using. So, therefore, by modifying the value of the K, we can incorporate the strain hardening effect. So, equivalent or effective stress refers to the yield surface as an isostate surface representing all the combination of the state that represent the elastoplastic transition. It is this is the isostress surface. Now, this represents the equivalent stress value. So, we can say this is a single numerical value, but that single numerical value is a function of sigma 1, sigma 2 and sigma 3, but if we follow the von Mises yield surface condition, then it is the having functional form of this one. So, this called K value or sigma bar, this is called the equivalent stress, that means one single value which is a function of all the principal stress components, and of course, this functional form can change if we follow different kind of the theory also. For uniaxial tensile testing, K already discussed twice sigma bar square, and von Mises yield functional become this one sigma bar square equal to 1 by half these things, but this is for uniaxial tensile testing, we can define this value. This is the yield surface, and that yield surface in the form of the sigma bar square, and of course, this sigma bar, if we say what is the sigma bar value, then we can say root over half of all this expression sigma 1 minus sigma 2 square. So, this is the equivalent stress if we follow the von Mises yield condition. Similarly, flow rules and the normality conditions that also exist during yielding and what way we can define the how the yield surface evolves, but the sustainability of the yield surface during the plastic deformation, continuous deformation, we need to put some kind of the normality conditions in the plasticity model also. So, this yielding, the ratio of the resulting strain, now we try to look into the strain condition. Resulting strain depends on the stress that causes the yielding. So, therefore, the relation between the plastic strain and the stress state are called the flow rules, but flow rules what we can represent that d epsilon increment of the strain is the plastic multiplier, basically d lambda some constant term, and d lambda is arbitrary constant, and df by d sigma j. So, therefore, the increment of the strain depends on the basically the state of the stress. So, suppose this is the yield surface for a particular situation which is represented at the yield surface, and this yield surface is represented by f, and f equal to k, that is the k is the functional form of the sigma 1, sigma 2, sigma 3. Now, normality condition for these cases can be represented what is the increment of the strain in a particular direction. So, this value increment of the strain value that should follow this multiplier and this how the d delta f by delta sigma ij. Now, if we follow this equation sigma bar square equal to half of this thing, we can find out what is the increment of the strain in particular direction, d epsilon 1 equal to d sigma by, I think here we can see the delta sigma by, it is a functional form by delta sigma 1. So, here we can find out the derivative of this one with respect to delta sigma 1, we can find out this is the expression. Similarly, d epsilon 2 equal to this is the expression, d epsilon 3 equal to this is the expression. Now, of course, in these cases the material value remain unchanged. So, therefore, the elemental d epsilon 1, d epsilon 2 and d epsilon 3 should be 0. That can be proved also if we try to there is no change in the material volume during the deformation process. Now, this rule says that direction of the d epsilon, that which direction the increment of the strain is independent of the d sigma. It is not necessary that they should be both should be the same direction. So, therefore, d epsilon is a vector normal to the yield surface, that we already defined, that we define the d epsilon is the normal to the yield surface f, and d lambda is the arbitrary constant. So, therefore, this deformation behavior or increment of the strain depends on the what are the arbitrary constant we are considering, and of course, it depends also at the stress state for a particular situation. This is normally called the normality condition in the plastic deformation situation. Now, we can find out the real stress and strain ratio during the looking into the normality conditions for uniaxial tensile testing, in particular the uniaxial tensile testing. What we can find out this normality condition, that x1 direction sigma 1 equal to sigma, for example, sigma 2 the some stress value, sigma 3 equal to 0. So, in these cases d epsilon 1 equal to this, similarly d epsilon 2 equal to this, d epsilon 3 equal to this for uniaxial tensile testing. So, in this case the increment ratio of the incremental strain is 2:1 -1:1. Similarly, balanced biaxial tension sigma 1 sigma 2 equal to sigma and sigma 3 equal to 0. In that situation, we can find out epsilon 1, epsilon 2 and d epsilon 3 is like that, and the ratio is something like that 1:1:-2. So, different during the deformation. So, ratio of the different strain components are different for the different deformation behavior, and that this ratio actually valid if we follow some kind of the normality condition during the plastic deformation process. Now, strain hardening effect, what we can incorporate the strain hardening effect during the plastic deformation behavior. So, strain hardening, the plasticity with the strain hardening, we can say that von Mises yield function not explicitly mention models about the strain hardening effect, because we say that k equal to as a functional form of sigma 1, sigma 2, thing like that. But what a k evolves, that is not well defined. So, if we follow the isotopic hardening for a 3-dimensional stress situation, a 3-dimensional plasticity, then sigma bar evolves in that way also. So, this is the functional from 1 f1, and then it evolves from here to here, and that because of the this value or this depends on the strain hardening, and this is all equivalent equal way it evolves from initial strain yield point to the next yield point due to the strain hardening effect, then This is this type of this is called the isotropic hardening. Now, kinematic hardening also possible. The yield surface size and shape remains the same, but the location actually translates. So, suppose this is the initial yield surface. Now, initial yield surface here it evolves next, it actually translates from one position to another position. So, therefore, this kind of hardening effect is called the kinematic hardening, and of course, this is situation arises when Bausinger effect is important, or there is a change of the stress state or abrupt reversals of the strain path takes place. This is the kinematic hardening model and this is isotropic hardening model, but in practically most material model, material behavior may follow combining of the isotropic kinematic hardening model, and it becomes more complicated when we combine all this material behavior. Now, we look into the work hardening and effect or necking effect during the process. So, we have already discussed that 3-dimensional stress state, and in terms of the principal stress, and finally we can make at the equivalent stress value, and that equivalent stress most of the cases we can say the equivalent stress at a single dimensional stress, they can in most easiest way or simple way we can represent the stress in stress strain in terms of this equation. So, where K is the strength coefficient, and this is called the Holloman type of the equation, that is simply relates the one dimensional stress to the one dimensional strain. It may be like that in 3-dimensional situation, this is the equivalent stress and this is the equivalent strain, and that equivalent stress and equivalent strain is related to in this form and a single value. So, therefore, K is the strength coefficients and N normally represents the strain hardening effect and work hardening effect. So, now in the logarithm, if we put in the logarithm scale and sigma equal to ln K plus N ln epsilon, then we can find out this is the expression ln sigma equal to ln K plus N ln epsilon. So, therefore, in this case this is the equation of most convenient simple way to represent the relate between the stress and strain. But in actual deformation process of the this thing, if you look in the stress strain diagram, if we assume the neglect the elastic component, if we represent only the plastic behavior. So, this equation K epsilon to the power N. Now, up to certain point there is a uniform deformation, and once uniform deformation at this point the necking starts in a deformation of a particular sample. So, therefore, when the necking starts at this point, so at the necking point of maximum load, actually if we look into engineering stress strain diagram, the necking point, the maximum load and localization of the stress. Necking means there is a reduction of the cross section and localization of the stress. So, therefore, competition between the work hardening, that means large deformation means it is tried to work harden more, that means strength level also increases, and at the same time the reduction in the cross section area, they are competitive with respect to each other, but there is a reduction of the at this point. So, that represents the in load deformation curve in engineering stress strain diagram is the optimum slope. So, therefore, at this necking condition mathematically we can find out that change of the force equal to 0, dF equal to 0. That means slope equal to 0 at this point. Now, if dF equal to 0, so therefore, F can be represented in the load is just stress into a cross section area. So, that means d sigma A equal to 0, that is the condition of the necking. Now, d sigma A can be represented this A d sigma or sigma dA equal to 0. From here we can d sigma by sigma equal to minus dA by A, but dA by A can be represented if we see during the plastic deformation also we can assume that there is no change in the volume. So, when no change in the volume means dV equal to 0. So, dV, suppose V is the cross section area of a cylindrical component A, cross section area L equal to length L. So, therefore, dAl equal to 0, therefore, we can decompose into AdL by LdA equal to 0. From here we can find out that dA by A equal to minus dL by L. So, minus dL by L is the elemental strain of a particular component. So, that we put it here, and here we can put it this value, we can find out this sigma. So, d sigma by d epsilon equal to sigma. So, this is the conditions, that condition is called d sigma by d epsilon equal to sigma. This is the condition for the necking for a particular deformation of a particular component. Now, of course, this during this necking point it is assumed that it is acting as a equivalent load or single axial single direction load is acting on this particular component. So, now if we assume that stress is related to strain by following the Holloman's type of the equation, if we assume the stress strain relation is this, of course, stress and strain relation may be a different equation, but if we assume this is the relation stress strain, then what will be the necking condition. So, then if we follow from here d sigma by d epsilon equal to k n epsilon n minus 1, but we can find out that which is equal to, see, this is the expression, and then but d sigma by d epsilon equal to condition equal to sigma, and sigma equal to k epsilon to the power n. So, therefore, k epsilon to the power n equal to this. From here we can find out that n equal to epsilon, that means this is called the consider a criteria, and that criteria actually established the necking condition, but this criteria comes assuming that stress strain relation follow the Holloman type of equation. But remember that if stress strain relation is something different, then this you may not find this kind of condition, because we can start with this expression, and in this expression we can assume some stress as a function of strain, but different expression. If we put this expression here, then we can find out the necking condition. But for this particular situation, if you follow the Holloman type of equation, this is the considered condition. We can easily explain using this graph if we look into that, and this is, suppose this is the true stress strain diagram here, and of course, this represents the slope d sigma by d epsilon. Now, this if you d sigma by d epsilon greater than sigma, particular situation if greater, this is the sigma curve. So, if this slope is greater than this value, slope is greater than this, slope is greater than this sigma, this side, this indicates the before necking, and d sigma by d epsilon less than sigma, that means d sigma by sigma is less than sigma, that actually indicates the this side is the necking situation. Now, we can do further calculation also, that work hardening. So, maximum load here we can put, if you use the Holloman type of the equation, the relation between stress strain. So, in these cases the considered condition is this one, sigma equal to n. Now, what is the maximum load? Actually, that means necking condition, the load becomes maximum. So, at maximum loading condition, stress equal to k epsilon to the power n, then k is this value and epsilon equal to n. So, k n to the power n, this is the condition, and of course, we can find out the true engineering stress and true strain, and because here we can, when using this relation sigma equal to k epsilon to the power n, actually we are using the value of the true stress and true strain here. So, therefore, the relation between the true stress equal to engineering stress into 1 plus engineering strain. This is the relation between the true stress and engineering stress value. So, here if we put this value sigma t and epsilon to the power n here, or engineering strain equal to true stress, engineering stress equal to true stress into e to the power minus strain. So, if we put this value, we can find out this is the expression, and from here sigma e can also be estimated, sigma equal to sigma t actually sigma t equal to k epsilon t to the power n. So, therefore, k n to the power n, because here epsilon equal to n, t equal to n. So, to the power n exponential to the power n. So, now here you can find out this expression. So, there you can find out, so all in terms of the known material parameters, strength coefficient, n hardening coefficients, and E and n, in terms of that we can find out. Of course, within this stress strain diagram we can find out the what is the work done per unit volume is a simple relation between it is the stress curve, strain, stress. So, here integration of the stress d epsilon n, from here you can find out the expression for that, and we can find out this expression work hardening and necking phenomena in this particular case. So here you see all this expression is basically this epsilon to the power n, but if we know epsilon equal to n, so we put epsilon n n to the power n plus 1. So therefore we can do this kind of sample calculation, and if we set the criteria for the necking conditions, and if we know the relation between the stress and strain, we can do all this kind of further calculation. Now even standards sensitivity can also be used most of the analysis in the engineering problem. So like what you can represent the Holloman type of equation k equal to k epsilon to the power n, but strain is the strain hardening coefficient, but similar we can represent the strain rates where k dot is the strength coefficients maybe or some constant value, and epsilon dot. So epsilon dot equal to the strain rate here to the power m. So m is the standard sensitivity index. Now in logarithm scale we can find out this is the expression, and in logarithm scale m is the slope, basically slope of the stress versus strain rate curve. So if we find out the slope particular point, we can find out what is the m value here. Now if we have the two different situation, the different value of the sigma 2 and sigma 1, experimental also we can do the different value of the sigma 1 and sigma 2, we can estimate corresponding strain rate 1 and corresponding strain rate 2, we can estimate the value of m also, because this m is the very practical useful parameter for a particular material, and experimental we can evaluate. For example, suppose strain rate can be represented like that, d epsilon by dt, change of this thing, d epsilon can be represented like that, d epsilon equal to elemental length with respect to original length. So dl by L by dt. So dl by dt y 1 by L, dl by dt is simply velocity v by L. Now if we look into actual in a universal tensile testing machine, so here we control the cross head speed. So when you conduct the experiment at the two different velocity, means two different cross head speed, and length of the sample remains the same at the two different cases. So now once the length of the sample is the same, and if you conduct the experiment two different strain rate, that means two different cross head speed, then we can find out the two different strain rate value, ratio of epsilon 2 to epsilon 1 equal to V2 by V1, assuming the L2, that means L equal to constant. So here this graphical you can represent this V1, and this is the two different cross head speed, and that ratio can be easily estimated, and if you put this value here, we can easily find out the value of the standard sensitivity index. So this way we can, through simple experiment, we can find out the value of the m, and then we use this m value for a particular model, stress model, when there is a effect of the strain rate in a particular situation. Now of course if you see, we have used the two different coefficients, one is the n work hardening or strain hardening coefficient, another is the m is the standard sensitivity index, and of course physical interpretation of the n and m are different in these cases. So of course the very work hardening effect is only the n strain up to uniform strain. So basically up to the uniform strain before necking, the value of n is more important. Therefore in that cases stress k epsilon to the power n is the most suitable equation there, such that there is effect of only the strain hardening. But above, beyond the, once the necking start, in that cases the strain hardening effect is not significant, rather strain rate sensitivity is more significant there. So therefore beyond the necking point, we represent the stress model is the epsilon to the power m dot is more relevant. So therefore, but actually in some material, and depending upon the material deformation behavior, the model can also be done considering the effect of the both strain rate effect as well as the strain hardening effect. So in that cases the expression can be modified like that, sigma equal to k epsilon to the power n and epsilon dot to the power m. So thank you very much for your kind attention.